So here's a vector. This just illustrates that, and this is a true statement about decision tree learning, although we didn't talk about it in the context of decision tree learning, is that in many cases in supervised learning in real settings, you're going to have unknown values. You're not going to know the value of a particular attribute. This is just something I've been using, 1, -1. You could think of this as yes, no, in the recommender system we talked about on Tuesday. But in some cases, you're not going to know a value. You won't observe it. It won't be part of the, so you'll be looking at a row in the training data and there'll be no value for this attribute. And there might be ways of representing that. Here I've just chosen to represent an unknown value as 0. In the naive Bayesian classifier, we would have, and in decision tree learning, although the methods are much more complicated, we have to have a way of dealing with unknown values, both in the training data and the test data. And there are a couple things you could do. In some cases, when something is unknown, it's actually predictive. So in medical diagnosis, for example, if a patient has been seen by a physician already and they've got a battery of lab tests, let's say you don't know what recommendation the physician has actually made for this patient. You just know that as part of this patient case history, this lab test is not present. So you don't know the glucose level. You don't know the A1C level of this patient because the physician did not order that test. In that case, if you're learning from the data after the physician has seen the patient and you see the patient case history, the fact that that feature is not known is predictive because an expert has decided that it's not relevant. Okay, so the lack of A1C in a patient case history of someone that's been seen by a physician already, a competent physician, is predictive that they do not have diabetes. Okay, so in some cases, unknown values are in fact predictive and we would want to keep them as such. But in other cases, and typically they're not going to be predictive. You just don't know the value. And so we would probably just not compute that probability. Okay, but in some cases, we might compute the probability of unknown given a particular class. The probability of unknown given diabetes. The probability that A1C is unknown given diabetes is probably low. But the probability of unknown A1C given a healthy patient, a demonstratively healthy patient that's been vetted by a physician is probably very high. The probability that A1C is unknown in a healthy patient because physicians just don't go around ordering A1Cs for people unless they exhibit symptoms. So you might choose to omit the probability, but in some applications you might actually choose to include it in your computation. There's also the problem we have to worry about in the naive Bayesian classifier and to some extent decision tree induction, because decision tree induction computes probabilities too, is the probability of zero probabilities. So let's say that you've just seen, the training data that you've seen is not a massive amount of data. There might be certain combinations of classes and values that are 0 because you have never seen them in the training data, but they are still theoretically possible. They are still true about the world as a whole. They still can exist. A conjunction of values can still exist. In the representation of the naive Bayesian classifier, a given joint probability may be 0, but then you may see it later in a test item. Even though you didn't see this in a training item, you still see it in a test item. But if you didn't see it in the training item and you literally interpret this ratio as 0, then what will happen is one of the probabilities in your series will be 0, and the whole joint probability will go to 0 as a result. And so when you really implement a naive Bayesian classifier, you'll typically use pseudo counts. And a pseudo count is going to be simply adding on an additional increment, constant increment to the counts. So when I compute the probability of V sub ij given ck, I don't compute it as simply this count divided by this count, but I compute it as this count plus 1 divided by this count plus 2. So it will never be 0. If this is 0, this will be at least 1/2. This ratio will be at least 1/2. And if you don't know anything else about the data, that makes some sense. If you've only got two options, saying that the probability of this given this, Vij given Ck, is 1/2, and the probability of and this is in the case of a binary value classes, and the probability of some other combination of Vij given Ck is also 1/2, or 1/3, or 1/4, depending on what the number of classes are and the number of values are. But in the case of binary variables and binary classes, we would add 1 to the numerator and 1 to the denominator. If these are initially 0, this is going to be 1/2. And that's what we're going to use to make a judgment. But in the case where this is large and this is large, the plus 1 and plus 2 are going to have negligible effects. Okay, and so the idea is you start off with this, a pseudo count will start you off with a small bias and a predetermined value, but as you collect real data on this combination and real data on this row, as the number of rows goes up here and the number of rows goes up satisfying this condition here, the plus 1 and plus 2 no longer have a substantial influence. And so the data, the actual data you see, dominates the computation. So that's another trick that you've got to use in computing using the naive Bayesian classifier. Okay, so